Now, when I started the section, I mentioned that some of the CPU time numbers in Task Manager are suspect. And in this section, we're going to look at how to get a better idea of where the system is spending its time. One of the things right away that may cause you to miss some activity in the system is the fact that Task Manager rounds the CPU percentage. So let's take a look. Here's Task Manager's list of the CPU activity percentage. And actually, it truncates. It doesn't round. So something that's taking 0.9% shows up as 0. 0.9 shows up as 0. Process Explorer has an option, it's not on by default, to show fractional CPU time. And I have that enabled. And the fractional CPU just shows a little bit of resolution. So for example, Explorer.exe, in the case where it shows up as 0.9, would show up as a 0 in Task Manager. You wouldn't know that it's running. But the whole CPU time accounting stuff is based on a mechanism, and this is not something unique to Windows. It's based on a mechanism that is in effect sampling what's happening on a periodic basis. Windows has a interval clock timer that it programs at boot time that interrupts the processor by default every 10 milliseconds on 32-bit systems. On x64, 64-bit systems, it's usually 15 milliseconds. There is a sysinternals tool where you can check the clock resolution. I'll go run that now. It's called ClockRes. And mine is running at about 10 milliseconds. And that's not something you can configure. That is set by the HAL, which is a low-level component that the OS loads. So every 10 milliseconds, the system is basically saying, who's running now? Who's running now? Who's running now? Who's running now? So what happens if 25 threads wake up, run, and voluntarily enter the wait state in between the 10 millisecond pulse? The system then is unaware of that activity. This interval was chosen in 1990 when NT was running on a 386 50 megahertz. Well, CPU speeds have changed a little bit since then, yet the interval has not changed. So what's been happening more and more over the last few years is that threads are never running even close to 10 milliseconds. They're doing their work and voluntarily entering the wait state. When a thread enters the wait state, and there is no other thread in the system that is waiting to run, the system switches to a thread called the idle thread, which shows up in a process called the idle process. Now, in a multi-CPU system, there's one idle thread per processor, because one processor could be running a real thread, another processor could be idle. So more often than not, every 10 milliseconds when the clock fires, who is the running thread? The idle thread. Which is why if you look at the CPU time accumulated on most Windows boxes today, the majority of the time has been accumulated by the idle process. So your system, if you check that at 9 in the morning and check it again at 5 p.m., could show up as being virtually idle the entire day when in fact it was busy all day. Because when the clock fires, more often than not, the idle thread is running. Now obviously, if you're running a compute-bound thread, video rendering, you're using Photoshop, some computational intensive thread, then that thread is going to be running when the clock fires. But on systems running a mixed workload, file servers, SQL servers, and desktop systems, threads run for such a short interval that they're often not running when the clock fires. That explains, if I sort the other way, how we have processes that have no CPU time. Their threads were never running when the clock fired. Now, again, Task Manager is truncating. So many of these are really 0.1, 0.2, 0.5, 0.9. They all show up as 0. But in some cases, they really are 0. There are threads in these processes that have never, ever run when the clock fired. And I could prove that if we could look at the thread details. So I'm going to use a tool that is from Microsoft called PStat. PStat has been around for a long time. It's part of the 2000 resource kit, and it's part of the XP support tools. By the way, the where command that I'm using, you know where is? Where is where? Let's ask where is. Where is in the 2000 resource kit. And all it does is take a file name and look in your path. And I like it because it reminds me where things are. In fact, I forgot where is. So PStat is in the XP support tools and the 2000 resource kit. All right, let's look at the output for PStat. PStat has first yet another version of the process list. So if you look at the names on the right, those are image names. So that's the process list with some counters. And then after it shows the processes, it enumerates the threads within each process. So now we're looking at thread details within a process. Now I'm going to stop and pick, let's pick, all right, here's a service host. Here's a thread, a single thread within that service host that has accumulated literally no CPU time. If you look at the two time columns, user and kernel time, and those two time buckets are how Windows keeps track of what mode the thread is running in. Threads running in user mode are executing application code. Threads caught running in kernel mode are running OS code, OS or driver code. So when the system interrupts itself every 10 milliseconds, if it interrupts a thread, it says, was the thread in user mode running user code, or was the thread in kernel mode running OS code, and it increments either of those buckets. That's a thread that was never running, ever, when the clock fired, because its CPU time is really 0. However, do you see a column that suggests that, in fact, the thread has run a number of times? Anybody see a column that would suggest that? It's the third column. It's the context switch count. The context switch count, and this is mentioned on the slide, is the number of times that the thread was selected to run. So again, when a thread is selected to run, its context switch count is incremented. Every time the thread begins to run, the context switch count is incremented. That is not susceptible to some interval-based timing mechanism. But the number of context switches doesn't tell you how long it ran. It tells you how many times it began running, not how long it ran. But it is an interesting way to get an idea of thread activity. For example, looking at this process, I can tell that the thread that never ran really ran 209 times. So taking that performance counter, Mark has produced kind of a sum of the context switch count that you can use in a way to detect thread activity in processes that are running in between the clock pulse. And he calls that the context switch delta. And basically, here's how it works. He adds up the number of context switches in a process. 1 second later, he adds up the number of context switches in the process. And he subtracts them. The delta is the number of context switches that occurred in the process on whatever refresh interval Process Explorer is configured to run at. So he's taking this core performance counter and coming up with a number that shows the differences in the number of context switches. So let's add that column, and we'll notice activity in processes that, if you looked at the CPU percentage, show up as 0, but in fact their threads are running and running and running and running and running. They're just running for such a short amount of time, they don't show up on the radar. So I'm going to go to the column selection, Process Performance tab, and add the context switch delta. And I'm going to drag that column over next to the CPU column so that we can see them side by side. And immediately, we start to see some processes, if you look on the lower part of the list, which according to the CPU counters aren't running. But if you look at the context switch delta, clearly there's activity. Take, for example, PowerPoint. PowerPoint occasionally has some threads that are waking up and running. I just saw an 8 there a minute ago. Now nothing's happening. But look at Internet Explorer above it. Internet Explorer has threads that are running, has a thread, or maybe more than one thread, that's running twice a second. And you kind of have to ask yourself, why is Internet Explorer consuming CPU time when it's not in focus? I'm not surfing the web right now. Or if you look down at the Run DLL 32, remember that was from the time-changing applet. Why does that process have thread activity when I don't have the window in focus? Part of the reason for this is, unfortunately, sloppy programming. Apps who have threads that are polling, checking if something is changed, checking if the registry has changed, checking if a file has been created or deleted. And that is pure, wasteful, sloppy programming, because the fact that these threads in these other processes are waking up and running and running and running is taking my CPU away. It's stealing CPU time from me. If I'm trying to render a video or compile an app, and I have these other threads that want to run for no good reason, I'm losing that CPU time to them. It is also wasting memory. Why? Because the fact that the threads in these processes keep waking up to run briefly means that the RAM that contains the code that they're executing is effectively pinned in memory, and the OS can't use that memory for something else. As opposed to what should be the case, what state should a thread be in a process that is not being asked to do any work? If you think about it, what's the ideal state that every thread in the system should be at when it's not being asked to do work? Waiting. Threads should be waiting and not waking up and running randomly, wasting CPU time and wasting memory. Also, it reduces the effectiveness of the per CPU memory caches. There's several negative consequences to that. Now, what becomes more dramatic is if I sort by the context switch delta column. And now I've brought up on the radar exactly the processes that have thread activity. And you start to look at some of these and say, what's going on? Now, this Avant browser is running so much that it's actually taking up CPU utilization that shows up on the radar, 25%. I have, if you happen to see, a huge backlog of web pages that I've opened to read later. And many of these web pages have animated GIFs. So it's got threads that are updating animated GIFs. Except, why is it doing that when the window's not in focus? Well, maybe you could say that's not the most efficient. Other examples. Outlook. What is Outlook doing? 75 context switches a second. I'm not using it right now. I'd like the threads to be in the wait state until I switch back to the window, thank you very much. But I love Outlook. My modem applet, that was the XE that we saw was owned by the modem vendor. 10 context switches a second. Do you see any phone cord connected to my modem? Nothing. So, I'm not trying to blame any particular vendor. Microsoft is also included. This is sloppy programming. And there may be nothing you can do about it. Although there is going to be something I'll mention later. I'll just mention it now and remind again later. There is something you could do about a process that is having needless context switching. Anybody have an idea? What could you do to get rid of that activity? Kill the process would be a bit severe. Take, for example, Avant browser. I've opened up 50 web pages to read tonight. I don't want to kill the process. What if I did this? He's out of there. In fact, he's dropped off to the end of the list, and you can see it's highlighted in kind of a gray. Suspending the threads in a process is kind of a neat tool to be able to do. That's using a standard Windows API, by the way, suspend process. It basically puts the processes on ice. It puts anesthesia into the patient. It doesn't kill the process. The threads are suspended. If they were running, their state is saved, and they'll run again later when I resume the process. And so that's something you could do to temporarily put a process that's wasting CPU time on ice. And now I have 25% of my computer back without having to kill the thing. My only warning about suspending processes is if you suspend a process whose threads are somehow in the loop or in the path of you doing something else, it is not unusual you start something and it's hung. It's hung because there's some resource that one of the threads in another process you suspended has blocked. If that happens, go resume that process, get your new thing started, and go back and suspend the other process. You wouldn't think that that would occur with unrelated processes, but there are some pieces of Windows library code that may own resources that if you suspend the process, the resource is locked and can't be freed until you resume the threads. So, the context switch delta column, I think it's a really interesting number to look at. It is a very different view of CPU activity. Again, look at this list. Of the 8 or 9 processes that are running, only 2 are showing up on the radar when it comes to the CPU column. So to me, the context switch delta is like a radar gun that lights up the threads that normally are flying below the radar. The time spent servicing interrupts is not charged to any thread in the system. So every 10 milliseconds the clock is firing. It's checking what's happening now, what's happening now, what's happening now. If the system is in the middle of a device driver, which is servicing an interrupt, that is not charged to a thread because drivers aren't threads. Interrupt service routines that are called as a result of a hardware interrupt are not associated with any thread in the system. And Windows charges interrupt time to two performance counters that, taken together, form interrupt time. And the two performance counters are interrupt time and DPC time. I'm bringing up Performance Monitor. And if you just click the plus sign, these two counters are basically in your face because they're part of the core Windows CPU time counters. Now, it's outside of the scope of the day to talk about the difference between interrupts and DPCs. If you're interested, it's in the book. Effectively, DPCs is the second phase of an interrupt. Interrupts have two phases, the interrupt and the deferred procedure call. So for today, let's just lump them together and say interrupts and DPCs represent interrupt time. So when an interrupt is in progress and the clock fires, it charges that time either to the interrupt or DPC time of the processor. If you look at the performance object on the top of the screen, it says it's the processor object because, again, on a multi-processor system, one CPU could be in the middle of an interrupt, another CPU could be running a thread. So each processor has its own interrupt and DPC time counters. So how can you detect this? How can you look at interrupt time? Well, Performance Monitor, this tool, lets you look at interrupt and DPC time. But what's quite odd is that Task Manager, ready for this? Are you sitting down? Task Manager includes interrupt and DPC time with the system idle process. It adds idle time, plus interrupt time, plus DPC time, and calls it idle time. So if you have a device that's going crazy generating heavy interrupts, you bring up Task Manager, your system will appear to be idle. Now, if you looked at it with perfmon, you'd see interrupt and DPC time separately. So in Process Explorer, Mark added in the process list two lines for interrupts and DPCs, so that the time spent servicing those important pieces of system execution will be shown on the map. Those are not processes. Let me say it again. Those are not processes. Interrupts and DPCs are not processes. But at least there's a way to look at that separately from the idle time and separate from other thread execution. If you look at the context switch delta column, those aren't context switches. That's the number of interrupts per second. So where it's reporting the context switch delta, if you're using that, that's the number of interrupts that occurred in the last second or the number of DPCs that occurred in the last second. So that's, to me, an important breakout of performance data. Now, if I go start up something like Windows Media Player and play some music, look at the interrupt time. It went up some, I think. DPC time has gone up. Now, obviously, we know it's the sound card, right? But looking at this alone, we don't. We just know that there's interrupts happening. Windows doesn't keep track of which driver was running when the interrupt occurred. So that takes us to the next slide of how can one identify the interrupt service routine or the DPC routine by driver name. Two approaches. One is a tool that Microsoft provides called the Kernel Profiler. And this is a free download. It's not part of the resource kit. It's not part of the support tools. And what the Kernel Profiler does is it interrupts the CPU periodically and keeps track of what the instruction pointer is, including cases where the instruction pointer is inside a driver at interrupt level. Now, if I don't know if my music is still playing. It's almost over, so I'm going to restart the song. Play. Is it playing? Play. Okay, we're playing. I'm going to go capture performance counters using the Kernel Profiler. And again, this is a free download for Microsoft. And there's an XE for 2000 and one for XP. I'm going to hit Enter. It's now collecting. So it's profiling the processor, keeping track of what the instruction pointer is on a very short interval. I'm going to press Control-C and stop the capture and scroll up. And let's look at the module names within the kernel where we spent time. 86% of the capture, which was, again, very short, was inside a module called NTOS kernel. That's the OS. 6% was in a module called SMWDM. These module names are names of drivers. Now, by default, drivers are in what folder? Where could I go look for the drivers? Windows, System32, drivers. And sure enough, there is an smwdm.sys. How could I look at the file properties for that? Bring up Explorer, go to smwdm.sys, and do a right-click Properties. By the way, I'm actually glad this happened. I just caught one of those cases. I'm trying to do something that is blocked by a process I suspended. Kind of odd that Explorer.exe is somehow connected to something that Internet Explorer has blocked. But watch this. If I go back and resume Avant Browser, right-click Resume, there's the window. See? I told you. Right-click Properties, go to the Version tab, and guess what? It's my sound driver. Okay, so kern rate is one way to get an idea of where the system is spending interrupt time. But even kern rate is susceptible to missing short-lived events because it's sampling. So although I'm not going to demo this, I'll just mention it. It's documented in our book. And there's a knowledge base article, by the way. You can get that online. XP Service Pack 2 and Server 2003 Service Pack 1 have a way now to trace every interrupt in DPC. Obviously, there's some impact on system performance. But it records in that system event log that I mentioned earlier, the Windows kernel event tracing, every interrupt and every DPC, which driver, and how long was spent in the interrupt in DPC. And using that trace RPT tool that I referenced, it generates a report that gives you a nice summary. We spent this much time in this driver and this much time in this driver. This was the longest interrupt service routine. This was the longest DPC routine. So that's a way to get an exact trace of interrupts. The kernel profiling is probably going to be accurate for a system that's having a heavy interrupt load. But it is possible that it's missing short-lived interrupts. And that's why I mentioned the tracing. One other aspect of understanding CPU time consumed by processes is how to deal with a process that is doing multiple things, like a service host, or the web server process, or a DLL host. So for a process that has several DLLs loaded that is consuming CPU time, the only way to really find out what's going on is to figure out which thread or threads are running and somehow determine what those threads are doing. And there's kind of two ways to deal with that: the invasive approach and the non-invasive approach. The invasive approach is using the Windows debugger, WinDBG, this is part of the Windows debugging tools, to attach to a process and use the debugging commands to inspect thread state, look at call stacks, that kind of stuff. The problem with attaching to a process, even if you select the option that says non-invasive, there's an option that says non-invasive on the bottom, it's invasive. In that, the threads are suspended while you're connected. When you attach to a process with the debugger, the threads are suspended while you're connected, which means they're not running. Now, that may be okay, because maybe you don't want things changing while you're looking. But in the case of looking at various system processes, like an SVC host, you probably don't want to suspend the threads while you're looking. So Process Explorer provides a non-invasive way to look at thread activity. And that's by going to a tab that we haven't looked at yet called the Threads tab. The Threads tab shows the threads within the process, their CPU utilization, and their context switch delta. So let's go take a look at a thread. For example, let's pick on notepad.exe. So here's a notepad process. Now, here's an example. I've got two notepads. I want to bring the window to the foreground for the one that I'm going to demonstrate with. So I'm going to use that bring to front. By the way, if you came in late, sorry about that. That's just a joke. So here's the notepad. I'm going to double-click and bring up the Threads tab. Inside Notepad are how many threads? There's only one thread. Remember we said Notepad is a dumb single-threaded program. There are two columns, the CPU time and the context switch delta. So those are configured by default. You can't change that. Now, that thread is in what state? Anybody see the state on the bottom, towards the bottom? There's the state. It's in the wait state. which is what you would expect. This is a thread that's waiting for what? It's waiting for user input. Now, we don't actually know that looking at the thread state. We just know that it's waiting. In a moment, we're going to see how we could prove that. This thread is waiting. So how can I make that thread run right now? Bring it to the foreground and do something with it. In fact, I'm just moving my mouse over the window, back and forth. I am not clicking on the window. And we see context switches and some CPU time. Now, when you see the CPU time number register, that meant that the thread was running enough that it was the current thread when the clock fired. But if I just move the mouse a little bit, we see context switches, but not always associated with recognized CPU execution. Now, why are there context switches when I simply move the mouse over the window? Those are sending mouse move messages. Notepad happens to ignore those, but it is getting messages. If I drag the window, then we see some noticeable CPU execution, because what is that thread having to do now that's taking a lot of time? Redraw. It's having to redraw the window. So looking at the threads in a process lets us see which threads are running. Now, what's this start address? That's the address that the programmer specified that the thread should begin running at. And in this case, we have some additional information about the function. We have the name of the function in the module. This name is coming from the fact that Microsoft provides symbol files for the Windows components. Those symbol files have the names of the functions in each exe and DLL and driver. Now, how is Process Explorer finding these symbol files? This is mentioned on the next slide. Process Explorer can be configured if you go to the Options, Configure Symbols menu item, to point Process Explorer to the on-demand symbol server on Microsoft's website. And that's that funny string on the bottom for the symbol path. And this is documented as part of the debugger tools. That symbol path says, SRV, look at the symbol server, store the downloaded copies in my local C symbols folder, and for symbols that you don't have, go to that website to download them. That's a string that you'll find in the debugger tools help. The first DBG help path is the location of the DLL that understands how to look for the symbols on the internet. dbghelp.dll is part of the debugging tools. This only works if you install the debugging tools on your box. And be careful, there is a dbghelp.dll that is part of Windows XP in the Windows directory. That one doesn't understand the symbol server. When you run Process Explorer, it will complain and say, symbols have not been configured, and it will only tell you that once. So if you dismiss that dialog, it's not going to remind you that they're not configured. Now, you don't have to have them configured. It just means that when Process Explorer goes to resolve function names, it may not be able to get the symbols, in which case you'll see to the right of the module name, you might see a hex offset. Now, that would be true if I looked at a process like PowerPoint. PowerPoint is running a piece of an image that Microsoft doesn't supply symbols for, which is why we see a hex offset. They only supply the symbols for the OS and not the layered applications. So if you see DLL plus some number or XE plus some number, it means the symbols aren't available. Or your symbol configuration is messed up and you're not getting symbols. So PowerPoint.exe, there's some function running a thread. There's some thread running this function. We don't know what the name of the function is, and we're not going to find out because we don't have symbols. All right, so back to Notepad. So in this case, we have the name of the symbol, WinMain CRT Startup. It's the main function for Notepad. So now you could see by looking in a multi-service process like an SVC host, you could see which threads are running, and then perhaps by the start address, pinpoint what piece of code is running in the context of that thread. Let's take an example looking at an SVC host, shall we? So I'm going to go open up an SVC host process. Let's look at the threads. And if you look at these start addresses, I'll pick on this one, fwcwsp.dll. Let's just pretend that was the thread that was consuming CPU time. Well, what is fwcwsp? WSP. If I click the module button that's down on the lower right, that brings up the file properties for the DLL. Can you see what this DLL is a part of? It's part of the firewall client. Now, there are other threads in the process whose start addresses by themselves may not mean anything. And that takes us to kind of the next slide, and that is looking at the call stack. So if the start address is some generic name that doesn't really identify what the thread is, you might find out the answer by looking at the call stack for the thread. The call stack represents the sequence of functions called from the beginning of the thread to where it is now, as illustrated in this diagram here. The thread started at function 1, it called function 2, which called function 3. Process Explorer is kind of taking a snapshot when you look at the thread stack. The thread is running. So you may look at the stack and see one result, and may look at it again and see another result, because it's not pausing the thread activity. So if we go back to this service host, I'm just going to pick on this. Here's a thread whose start address is some generic service control thread startup function in some Windows API DLL. Double-click and look at the thread stack. Now, the stack in time order starts down here and moves up. So the thread started at line 15, called a function at line 14, which called this, which called this, which called this. Can you tell, starting from 15 and working your way down, what service this thread is running a piece of? Line 15 doesn't tell us, because that's some generic thread startup function. Line 14 doesn't tell us, since that's some generic service startup function. Line 13 doesn't tell us, because that's the generic service host starter function. Line 12. Service main in what DLL? RPCSS. Now, what comes after that is kind of not interesting to me, because I've now identified that this thread is really running a piece of the RPC, remote procedure call service, which, if we look at the services, is what's running inside this process. So the call stack is a very, very essential piece of state that you may need to look at to figure out what a thread is doing. And Process Explorer makes it real simple. You can do it with WinDBG, but when you attach to a process with WinDBG, the threads are frozen. Looking at the call stack is also a great way to figure out why a thread is in the wait state. So let's go back to Notepad for a second. I said Notepad is waiting. We look at the state, it's in the wait state. And I asked you what's it waiting on, and you all said it's waiting on some user interface operation, and you were correct. But if we look at the call stack, we'll have proof of that. So I'm pressing the stack button. And again, the thread started here, which called this function, which called this function, which then made a system call, which entered the OS and called the system call implemented in a driver called win32k.sys, which happens to be the windowing system driver. The windowing system was moved to run in kernel mode as a loaded driver as of NT4. What system call did Notepad call? The get message system call. That's the system call to get a window message. And that called a function inside this driver, which called a function inside the driver to go to sleep, because apparently there wasn't a window message, so it's going to wait for one. And that called a function in the kernel to swap the context to another thread. Now, this is interesting because anytime a thread enters the wait state, that thread initiates the context switch to the next thread waiting to run. So imagine runners in a relay race with a baton. Each runner passes the baton to the next runner in the race. Relay race. The threads are passing the baton. So when a thread enters the wait state to wait on some resource or some I/O, it is responsible to give the CPU to the next thread waiting to run. So the last thing that any thread does before it enters the wait state is swap the context to another thread. That you're going to see is the last thing for virtually any thread in the wait state. So if you see the swap context on the stack, that just means it gave the CPU to somebody else. Why did it do that? You've got to look backwards. And for this thread, we can see, it's waiting on a window message. So the call stack is a very key resource to understand what a thread is doing. Here's a neat example where Mark actually solved a problem on his desktop looking at the call stack of the main thread in PowerPoint. The symptom that Mark had was he double-clicked on a PowerPoint file. 60 seconds later, PowerPoint appeared. and everything worked fine. So he wanted to find out what was going on during this 60-second delay. Now, using Process Explorer, when he double-clicked on the PowerPoint file, he saw PowerPoint.exe appear in the process list. So he knew instantly the process was being created, but the window didn't appear until 60 seconds later. So during that 60-second interval, he went and looked at the threads in PowerPoint. There was one thread in PowerPoint. He looked at the call stack. This was the call stack. Now, just looking at the call stack, without being a super rocket scientist, computer expert, what was PowerPoint trying to do? Connect to a network printer. Look at the call stack. PowerPoint. Now, again, line 10, we don't know what function in PowerPoint. There's a plus with a hex offset because there's no symbols. It called a function in what DLL? Line 9. MSO stands for Microsoft Office. And again, we don't have a useful symbol name because they don't provide symbols for Microsoft Office. That DLL called a function in a DLL that is part of Windows called winspool.drv. That is not a device driver, it's a DLL. Yet another different extension given to DLLs called OpenPrinter. It called a function inside itself called OpenPrinter RPC, remote procedure call. So that kind of implies a remote printer, which called a function in RPC runtime, which eventually, when we got to the end of the stack, ended up waiting on something. And because this is taking a snapshot of the call stack, this particular snapshot didn't show the fact that the thread had done the context switch. And the stack walking code that Mark is using is part of the debugger help DLL. And there are some weird cases where it doesn't quite give you an exact stack. But in any case, he could tell right away that PowerPoint was stuck connecting to a network printer. Turns out that all the Microsoft Office applications, when you start them, connect to every printer, even if you never print. Now, you might question if that's actually a good strategy. Mark had a printer configured, and the print server was messed up. So it was timing out. After 60 seconds, it would time out. PowerPoint would come up. But immediately looking at the call stack, he could determine that was the problem. He deleted the printer from his client, from his desktop, problem went away. So looking at the thread stack is another way to deal with hung processes. Something is stuck, go look at the call stack and find out why. If the thread stack doesn't obviously point to the root of the problem, and it's not your program, then what can you do about it? Well, don't just kill it and run it again. Make a snapshot of the memory space and get that to the programmer. Let somebody else deal with it. Because the programmer, if they could get into the process address space, hopefully could debug why this thread is stuck. And that's very easy to do with a set of scripts in the Windows debugging tools called AD+. It's actually a script that uses the command line debugger to go attach to a process, create a memory dump, and then disconnect. And you can do that to the process with or without killing it. And that's interesting if you have a server process that is somehow stuck. But it's not completely dead. So maybe there's one client of a server, he's stuck, but other clients are still working. So you don't really want to kill the server process because it's handling other people. Snapshot the memory space. Get the programmer to go look at that. Again, if the programmer comes on the system and starts to look at the hung process, what's the state of the process while the programmer is debugging? Frozen. So this is a way to snapshot the memory space, let somebody look at it offline. And that you can do with the debugger tools. It is in a frozen state while making the snapshot. So it uses the debugger to attach, makes a dump of the process address space, and then resumes the threads. Another tool that's actually built into Windows, let's say you don't have the debugger tools installed, this is something you can do on any Windows box because this is part of the OS and it's been there since NT 3.1. Dr. Watson. Dr. Watson 32 takes a command line argument, -P, and then a numeric process ID. So Dr. Watson 32 -P 42 attaches to process 42, makes a memory dump, and then kills the process. So that's just a point about Dr. Watson. It kills the sick process after dumping it. But at least you could make a dump on a system that maybe didn't have the debugger tools configured. Just one little note on the bottom of the slide. As of XP and later, the dump that Dr. Watson creates is a mini dump and not a full dump. If you run Dr. Watson 32 with no switches, I'm going to do that now, run dr WTSN32. You can look at the configuration, and if you notice the crash dump type on the top of the screen, I set my system from mini to full. That was a choice I made, because if there's a process hung on my machine, I want to get a full dump, because I know as a programmer the mini dump contains a very limited amount of information about the process state that makes debugging much more difficult for the programmer. So for example, when one of Mark's tools crashes or hangs, I get a full dump. I can send him a complete memory dump, which he can open with Visual Studio or WinDBG and go and basically perform an autopsy. The mini dump would be like performing an autopsy on a patient, but only being able to slice open the left hand. When they had a heart problem, it would be difficult to make the connection. So mini dumps provide a limited amount of state to the programmer. So if you're having a regular hang situation, you might want to change Dr. Watson to make a full dump. And then you have some more information to send to the programmer. Okay, so that's dealing with hung processes. Now, there's another process kind of like service host called the system process. And I'd like to talk briefly about the system process. If you look at the process list, what's different about the system process than everything underneath? The image name. What's different about the image name? No exe, because that process is not running a single executable on the system. The system process, which on my system, if I look at the thread count, has 76 threads. And on your system, it's going to vary. Depends on the number of drivers loaded and whether you're a server or a workstation. The system process is a container for pieces of the OS and pieces of device drivers that need to run as threads, meaning pieces of the OS that need to have their own life, the ability to run independently of user activity because they're performing some background housekeeping operations. So when the system boots, the OS creates a number of pieces of itself as threads. When some drivers load, they create pieces of themselves as threads. Normally, a device driver doesn't run by itself. It runs when you call the driver to do work. When you do a disk I.O., the disk driver gets called to initiate the I.O. It doesn't just wake up and run on its own. There are some drivers, however, that need to run on their own. And an example of that is the file server driver. So the example lab, if you look at the slide 50, here's an example demo that generates activity in the system process that when we look at the thread activity in the system process, immediately pinpoints who's responsible. So I'm going to go basically do a directory of my C drive over the network to myself. So let's go initiate that from the command prompt. dir big David C$S. So I'm doing a directory of my entire C drive over the network. If I bring up Task Manager, there is activity in the system process. See it? 27, 9, 7, 8. Now, looking at that by itself tells me nothing because I don't know whether it's a piece of the OS or it's driver A or B or C without going in and finding out which threads are running. And that's very simple to do with Process Explorer because we simply go to the process, the system process, and go to which tab? Threads tab. Now, there's a little pause here because I'm running some third-party drivers that have system threads. Process Explorer is going over the internet to see if there's symbols. There are no symbols for third-party drivers. So I could have configured Process Explorer for this demo to not go over the net, just to look on my C drive. Then it would have come up right away. So there are several third-party drivers, actually, that have system threads in my system. So this is going to pop up in a second. By the way, Process Explorer, if we could use Process Explorer to look at its own threads, we could see the thread that is waiting in the debugger help DLL. But because Process Explorer is stuck, I can't use Process Explorer to look at Process Explorer. Actually, I could run another instance of it. There we go. Now, if you were trying to look at activity of threads within a process, which column would you sort by, the CPU percentage or context switch delta, based on our discussion before the break? Obviously, the context switch delta, because threads are often running in between the pulse. Now, I think, did my directory finish? No, it's still going. Which driver has a thread consuming the most number of context switches? the file server driver. There it is, srv.sys. And the function is worker thread. The file server driver creates worker threads to run pieces of itself in the system process. If I didn't know what srv.sys was, what button could I press to help me out? Module. Go to the file properties, and sure enough, that is the server driver. Okay, so there's a quick way. Again, it's looking at the threads tab, sort by the context switch delta to immediately pinpoint what thread or threads are running. Okay, so that's it for looking at CPU usage. Just to summarize, we looked at the importance of the context switch count as a way to basically, with a radar gun, find threads that normally are flying below the radar in between the clock pulses. We looked at how to separate interrupt and DPC time from the idle process, which Task Manager considers to be idle activity. And we talked about tools to even drill down into what driver was responsible for the interrupt activity, the kernel profiler. Okay, 3 more topics for process and thread troubleshooting. I mentioned there were 3 basic pieces of state that comprise a process: the private memory, the security or access token. This was the third, the handle table. Every process has a list of the open resources or handles, and those could be files, folders, registry keys, handles to devices like the COM port or the serial port, parallel port, maybe TCP or UDP endpoints. And it might be useful to query this list to understand what resources the process has its fingers on. There's a couple of ways to do that. There's some tools that Microsoft provides. OH.exe has been around for a long time in the resource kit. XP now has a command line, open files command. Both of these tools, however, require that you reboot after setting a flag in the registry with a tool mentioned on the slide, gflags.exe. That is not normally set. And there's no problem leaving this set. There's no serious resource issue. So I'm going to run gflags, and gflags, if I use where, is in the XP support tools, which means it's also in the 2003 support tools. And there's a flag that I have set. It's the second checkbox, the maintain a list of objects for each type. And the tools will tell you you didn't have the flag on if you try to use them. Now, that does require a reboot. Process Explorer can query the handle table without this flag being set because it's using a different mechanism to get the data. It's using a device driver. So what could be interesting to look at when examining a process's handle table? Well, the first point to me is kind of just as if it's an application that you're supporting, being able to look inside a process to see what files are open and how they were opened and what registry keys are open tells you something about the app that you might not have been aware of. One example that's happened a couple of times is apps that are opening files that are on the local hard drive with a UNC path name. Due to some configuration errors, apps were opening local files using a network share. Well, that's not a very efficient way to get to local files. In fact, it's quite a bit slower. So just looking at a way a file was opened has helped me solve a couple of performance problems. Let's take a look at the handle table for a process with Process Explorer, and I'm going to enable the lower pane, or the lower half of the display. I had turned that off. It's on by default. And there's 2 views for the lower pane, the loaded DLLs, which we're going to talk about next, and the open handles. So if I turn on the lower pane and scroll down to PowerPoint.exe and look at the open handles, somewhere in this list is going to be the file that I'm showing you now. And sure enough, there it is. It's 1-process-troubleshooting.ppt in my C slides directory. That's an open file. Now, open files may not be files on the disk. They could be folders. For example, if I look at this command prompt, bring it to front, and look at the current directory. My current directory is in C Program Files Debugging Tools for Windows. If I look at the handle table for this process, there is a handle open to C Program Files Debugging Tools for Windows. You ever notice that if you have a default directory set, you can't delete that directory? Why? Because it's open. Now, if I change the directory to go to the root, it closes one handle and opens another. The refresh highlighting that we saw on the process list applies to handles. If I cd to the Windows directory, again, it closes one handle and opens another. So that's another useful thing, is looking at changes in the handle table. You do something in an app, it opens 5 files. That might be interesting to look at, especially if there is a bug called a handle leak, which means a handle is being opened but not being closed. And I've run into that. I'm sure some of you have as well. Apps that are opening objects but not closing them. The handle leak is pretty obvious if you're looking at the handle view, because what color are you going to see consistently? Green, green, green with no red. And it turns out that a process with a handle leak can do a very bad thing to the system. I'm going to run a test app that opens handles continuously until it can't open handles anymore. So that is the number of handles opened. We've had 400,000, 500,000, 600,000. This is a serious handle leak. We're up to 1 million handles now. If you look in the kernel memory section, can you look in the lower middle part of the screen, in the kernel memory section, do you see a number going up slowly? Which of those, between paged and non-paged, which is going up? Between kernel memory paged and non-paged, which is going up? Paged, right? Now I'm going to stop this thing, actually, or my system is really going to get quite upset. And by the way, if you look at the paged memory, it just dropped down. When a process exits, the system closes all the handles. So when I hit Control-C, 3.5 million handles just got closed in that process. The process handle table is allocated from an OS memory area called kernel memory, paged pool. We're going to talk about paged pool in the memory troubleshooting section. This is an app bug that can take down your box. Because if a process opens handles forever, it may exhaust kernel memory. When there's no more kernel memory, you can't create a process. Other apps may start failing. Now, it shouldn't blue screen the system. Something's wrong. If something blue screens, there's a bug in a driver, or maybe a bug in the OS. They're supposed to handle that gracefully. But it's not unusual to have bizarre app failures, because apps that weren't expecting to get no more memory start getting errors. And frankly, most apps just don't deal with that very well. So that's a little piece of about the NT kernel that I'm not happy to explain, that a non-privileged user application can effectively take down a server. On a terminal server, for example, if I was on a terminal server, I could run that program and effectively use up all kernel memory and stop everybody else from being able to do anything. So a handle leak, although it sounds like it's an app bug, is indirectly causing system memory utilization that could take the box down. But it's really simple to find out who's leaking handles. If the handle count, for example, I'm going to run it again. If you're looking at the system handle count, that's this number here, and it's unusually large or going up rapidly, how easy is it to find out who's leaking handles? Go to the process list, configure the handle count, sort by the number of handles, and sure enough, it's pretty obvious that there's this process with an unusually large number of handles. I'll go kill it again. Now, you're not going to see something with 2 million, hopefully, but you might see hundreds or thousands. With Process Explorer, then you could go and look at the handle table and find out, is there some entry repeated multiple times? Is that a handle leak? And then when you report the bug to the developer, you've kind of told him what the problem is, because you're now able to say, you have a handle leak. This is what you are not closing, sir or madam. Could you please fix the bug? And if they can't fix the bug based on that, they should find a new job. The other thing about the handle view is it's an easy way to find out who's got a file open. For example, if I go try and delete the PowerPoint file that I'm showing you now, so I'm going to go to the folder where that file was, and I'm going to delete it. Now, I'm a little nervous because this is my only copy. I have no backups. Shall I do it? Whew. The file's in use. Now, I could go use Process Explorer to search the handle table and find out who's got the file open. I'm going to put as the handle name .ppt, partial name, and bingo, there's a handle to something with .ppt in the name. go double-click, and that takes me to the handle in the process that has the handle open. There we go. Now, what about doing this? Right-click, close handle. That would be nasty, wouldn't it? Shall we do it to PowerPoint? Let's do it. I just closed a handle out from under the app. That's generally not a good thing to do to an app. Because if PowerPoint goes and uses that handle, it's going to get an error that it didn't perhaps expect. But because this is Microsoft Office, we have full confidence that when we go back to the PowerPoint slide, of course, it still works. It's resilient. It's self-healing. It's Microsoft Office. So, did PowerPoint reopen the handle? Let's go back and look. I'm going to search the handle table. Click search. In fact, it didn't reopen the handle, which means we just learned it's not using the handle to read the data, which it isn't. It's using memory map files. In fact, if we go to delete this now, you think we can delete it? No, because it's in use, but it's in use in a funny way. And this is a bug in the command prompt giving us the wrong error code, which we're going to talk about later. Using FileMon, we can find out what's really happening under the hood. This is a great example of an app. It's not unique to the command prompt, where it gets an error, but reports the wrong error. It's getting an error that it didn't expect and presenting the wrong error. There's no permission problem. I own that file. This is my laptop. I'm an administrator. I created that file. Don't tell me access is denied. That's not the problem. We're going to look under the hood later and see what's really happening. Okay, so those are some uses of handle view. And we did this example, looking at the differences, highlighting. The other view in the lower pane is the DLL view. So let's go back to Process Explorer and switch the lower pane from handles to DLLs. If you look at the list here, that's interesting. My PowerPoint file is in the list. By the way, that's why I couldn't delete it. So while there are files that end in DLL, this is more than a list of the DLLs. This is a list of all of the memory mapped files in the address space of the process. All of the memory mapped files, of which many are DLLs, of which one will always be the exe. PowerPoint.exe is somewhere in the list here. And memory map files are a high-speed file access mechanism that provide a way for an application to give the illusion to itself that a file is in memory when it's on the disk. PowerPoint, being an advanced application, uses memory map files to get to the PowerPoint data. It doesn't read the data with read calls. It makes a special call that tells the system, please, I want to map that file on the disk into this address in my memory space, and I'm going to pretend it's in memory and just access it as if it's in memory. And if it's not, page fault it off the disk on demand. So the memory manager in this case is doing the file I/O, not PowerPoint directly. Indirectly, PowerPoint is causing page faults to the PPT file. So that explains why when I close the file handle, it still works. It opened the file in order to memory map it. That's why there was a file handle. But it's not using the file handle to read the data. And because it's still in the list of memory mapped files, the PPT file, that is, that's why I can't delete it. Because it really is open. I got a different error code because it's not open as a normal file. It's in use as a memory mapped file. So, what can you use the DLL view for? Well, certainly it's interesting for looking at loaded DLLs. I'm sure you've all dealt with what Microsoft calls DLL. I don't want to say it. DLL-HELL. Looking at the DLL list for a process, especially if you have a case where it's working on one system and failing on another, just by comparing the version numbers and perhaps the full path might reveal configuration issues that cause the wrong DLL to get loaded. So I could add the path column here, and now I can see the full path of each loaded DLL. So if I save this output to a file, Process Explorer has a file save as, that saves the DLL list for the process or the handle list, and go and diff that or compare it to a working process from another system. I might point up some configuration issues in terms of DLLs that were loaded. That's another way to use that list is as a way to find out who's got a DLL loaded that you're trying to replace. So let's go back to that find. There's a find DLL. That searches the list of loaded DLLs, actually memory map files. So for example, if I search for notepad.exe, which is a memory mapped file, notepad.exe is mapped into two different processes because I'm running Notepad twice. So the find command could be useful to find out who's got a DLL loaded that you're trying to replace. So you saw me get the access denied error from the command prompt when I tried to delete the PowerPoint file. That's because that's what it reports when trying to delete a memory map file that's in use. That's the same error that it tells me when I try to delete notepad.exe. Why? Because notepad.exe is a in-use memory map file. Okay, last topic for process troubleshooting. This has become more of an interesting topic in the last year or two with the increasing march of spyware processes that seem to be appearing in more and more places, dealing with processes on the system that you don't quite recognize and you don't know how they got there. And what could be suspicious when looking at the process list is a process, for example, that has no version information. Now, we saw a couple of examples of processes that didn't have a company name or they didn't have a description. But that by itself doesn't mean anything because, like this little test app, which Mark wrote, reports itself as Microsoft Corporation, but in fact is running some exe in my C sysint Solomon folder. So what could we do to kind of determine what this app is? Well, Process Explorer makes it simple to go do a internet search. So right-click MSN search. Checking the parent process. Remember I said this morning that just looking at who made the process could, in a way, give you a clue as to where you should look to see why it's there. Who's the parent of this logon HLP? Well, actually, it has no parent. That was one of the processes that was... Oh, there it is. Sorry. Its parent was Explorer. That Explorer is dead. There is no 876. Remember I said my Explorer exited and restarted. But that was the parent before that Explorer.exe exited. So the fact that it was created by Explorer tells me either I started it or Explorer was configured to start it, which in fact it was. We're going to see that in my registry in a minute. It's in a little registry key that got started automatically at logon. So the parent process may be a key piece of information to understand who made the process. The other is to look at the handle table. You see some strange process on the system. What files does it have open? What registry keys are open? Maybe that's going to give you a clue. Now, if this process is like running and doing stuff, and you'd like to inspect it but stop it from doing stuff, suspend it while you look around instead of killing it. And you saw me demonstrate that earlier when I suspended the Avant browser process. In the case of some pieces of spyware, they have connections to external websites. So looking at the open TCP/IP endpoints might reveal a clue as to what it is. Netstat can show those endpoints. TCP view from sysinternals lists the endpoints. Process Explorer also shows that on another tab that we hadn't looked at, the TCP/IP tab. So let's go take my Avant browser process, for example, here. Well, MSN Messenger, actually, that's a good one. Go to the TCP/IP tab. Am I not signed in? Okay, I'm going to go sign in and watch the endpoints that are opened and where they're opening to. So we just watched Messenger get set up and connect to some remote servers on the internet, and it's maintaining this one connection to a Hotmail server, which is where part of the MSN Messenger service must be running. By the way, the call stack of the thread that opened the port is recorded now by XP, and Process Explorer can show that. So can the netstat command. That's interesting because now if you see a socket in a process that is doing multiple things, like an SVC host, you can find out which thread opened the socket, what piece of code caused that endpoint, to be opened. That's the thread stack But that's also available in the netstat command. There's a new switch, -v. This is an XP that shows the call stack. If you're still not sure what this thing is, go undress the XE. Take its clothes off. And by that I mean look at the strings inside the XE. Maybe there'll be some clues. There might be some URLs or some registry keys. Now there's a couple of ways to look at the strings. You can open an XE with Notepad. But if you do that, you're going to see all kinds of non-printable stuff, and it makes it hard to see the printable strings. So Process Explorer provides a tab for each process that shows the printable strings, and that's the Strings tab. Now, it doesn't know if the string is meaningful or not. It's showing it if it's a printable string. It's in the printable range. It's smart enough, though, to make 2 passes through the XE, because strings can be encoded in one of 2 ways, 8-bit or 16-bit, Unicode or ANSI. So it makes 2 passes through the XE and shows the Unicode strings and then the non-Unicode strings. So these are just random error message text. And that's something that alone may clue you into what it is, looking at the error message text inside the XE. There may be references to source file names if the programmer wasn't smart enough to compile it without debug. In fact, look at that. That's the location on Mark's desktop where he had configured Visual Studio to build the symbol file for this XE, because he gave me a debug build and not a release build. And so that string is inside the binary. So the Strings tab. But, you know, the strings in the XE may not be the answer, because a process consists of the XE and 1 or more loaded DLLs. So you may need to go look at the strings inside each DLL. Right-click, strings. Right-click, strings. There's also a command line version of strings from sysinternals that takes a file, any file, and dumps the printable strings. So there's 2 ways to look at that. That alone has helped me identify some spyware apps on a neighbor's system. My neighbor called me up and had some process in the list that I couldn't find any information on Google, MSN search. And when I looked at the strings, I saw definite evidence of spyware. There were URLs that it was making, that it wasn't connected to at that point, but might connect to. Now, looking at who started the process may yield a clue. If it's explorer.exe, somehow Explorer was configured to start that little fake spyware process when I signed in. So where would you go to look at what's configured to start when you log in? XP has a new tool called msconfig, and it's modeled after a tool that was in Windows Millennium Edition that has a tab called the Startup tab that lists apps configured to start at login. And it's showing values of various registry keys. Current version, run once. It also shows things in the startup folder. But the process that we identified on my system isn't in the list there. Let's go back and look. This process, logonhlp.exe, isn't shown in the list. And that's because this tool doesn't show all the places in the registry that can be configured for stuff to start at login time. Mark has a freeware tool called AutoRuns, which over the last year has, if you've run it in the past, get the latest version, because even just 2 weeks ago, Mark found yet another registry key that may contain code that is loaded at startup time. So it shows, we think, all the places that Windows looks for processes or DLLs to be loaded at logon time. So I'm going to run AutoRuns, and we'll take a look at the list. And the list of places the system looks is mind-boggling. It's amazing how many different places in the registry that the system can be configured to look at for things to start at login time. Where's the process? Hello. Auto runs? There it is. Right-click, bring to front. Okay. It was actually still querying And it's still querying right now. I'm pressing the escape. If you look on the bottom of the status bar, it says verifying ultramon.exe. Very bottom of the screen. Let me bring that up a little bit to the top. Move that up. There. I'm going to press escape to cancel that. You know what it's trying to do? Validate image signatures. I just pressed escape. It's canceling. And I'll show you the configuration option to turn that off. I had the verify code signatures on. Don't remember if it's on by default or not, which means every exe, it's going over the internet to validate the digital signature. And that's why it was taking a while to start up. So look at all the places in the registry. These are all registry keys that can be configured to load stuff at login time. That msconfig tool shows a small fraction. Now that little fake virus program, where is that? Anybody see it? I had deleted it actually in the last class. Let me put it back. Solomon, fakevirus.reg. Allow. By the way, Microsoft Anti-Spyware just caught that, but I'm going to allow it to be added to the registry. Yes. And I'm going to press F5. And sure enough, where's the virus? I was hiding the Microsoft entries. So now, one more time, F5. Obviously, now a much longer list, but I think we should see somewhere in this list. I just saw it. There it is. There's the virus. The logon helper application. So I was fooled by my own fake spyware. I thought it was safe to hide the Microsoft entries, and that's why it wasn't in the list. So this was a registry key, policies explorer run, that was configured to run this exe. So again, auto run shows several places in the registry that can be configured to load code. And many of these, by the way, are DLLs. Most people think of spyware being a process that is being started. It could also be in a DLL that's loaded in explorer.exe or some other system process. So when you get home, run auto runs, do an inventory, make sure you understand everything being started on your system. You may be surprised. And please go to the View menu and enable all of the various options because they're not on by default. By default, it doesn't show some of these other locations. I think these last three aren't shown. So that's it for looking at process and threat activity. I hope that was useful to you for getting a better idea to look under the hood, take a stethoscope, and figure out where your CPU time is going.